Welcome to our fourth unit of Unit 4, which again is on thermodynamics. This one we're talking about heat capacity and specific heat. So, the amount of heat needed to raise the temperature of an object by exactly 1 degree Celsius is called the heat capacity of an object. This is why certain objects will heat up faster and certain objects will heat up slower, because they have different heat capacities. For example, this is McDonald's apple pie. And if you've never had one, honestly, that's probably good. They're not that great for you. They taste good and all, but yeah. Anyways, if you have, you've often had a part where, especially if they're fresh, you take the apple pie and you bite it because you're thinking, oh, this crust is kind of warm, it's not that bad. And then you bite into the apple filling and it lights your mouth on fire. It's excruciatingly painful, and while tasteful, your mouth is on fire, and you're like, why did I ever do this? Eventually, you learned to bite a little bit and test the apple pie. That difference is because they have a different heat capacity. The crust has a much higher heat capacity than the apple pie filling. That means that it takes a lot more heat to make it hot, a lot more heat to raise its temperature. And while it will raise sufficiently enough to be cooked, the apple pie with that same amount of heat will have a much higher temperature. Thus, it'll hurt your mouth a lot more. So, the heat capacity of an object depends on both its mass and its chemical composition. Basically, the greater the mass, the higher the capacity. So, the bigger something is, the more heat it's going to take. And the stronger the chemical bonds, the greater the capacity. Which means the more tightly it's made. The stronger it's bonded, the more heat. Hopefully, you're getting it. An example is it would take a lot more heat to heat up this gallon of water than to heat up this bottle of water, because this has a higher mass. They're the same compound, hopefully, so their bonds are the same. Back to apple pie and crust, the main difference there is going to be the bonds, because they both weigh about the same. The crust isn't seriously heavier. Anyways, two main things, mass and chemical bonds. So, while that's all great, it's really kind of hard to compare everything by this mass, so we define what's called the specific heat capacity. Now, this is the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. So, if we took a gram of something and we figured out how much heat we need to raise it by 1 Kelvin, which hopefully remember is also the same as 1 Celsius, that is its specific heat capacity. So, the molar heat capacity is very similar. It's just the amount required to raise 1 mole instead of 1 gram by 1 Kelvin. Both are quite commonly used, but fortunately, they both deal with very similar things. So, to calculate the specific heat of a substance, or the specific heat capacity, you can call them both. You divide the heat input by the mass of the substance times the temperature change. Basically, you take the amount of heat that is required, but you got to divide that by however much it weighs and the actual temperature change. Typically, that heat will be in joules or calories, and it's represented by a Q. I really don't know why, but it's represented by a Q. Our mass is typically represented by an M, and our change in temperature, we'll talk about in a bit, is represented by a delta, that little triangle thing, T. Delta is actually a Greek letter. Congratulations, you know a different language now, or at least one letter of it. But nonetheless, our specific heat capacity is our heat divided by our mass times our temperature change. Oh, and it's right here. So the symbol delta refers to the change in something. In this case, change in temperature, but delta height, if you will, could be your change in height. Let's say you wanted to compare how much you grew from 4th grade to 5th grade. You'd be calculating your delta height. So delta T is basically our final temperature minus our initial, which typically we'll write as TF and TI, F standing for final and I standing for initial. So final minus initial. And to convert between specific heat and molar heat capacity, all you have to do is take your specific heat capacity and times it by its molar mass. That's it. And you know how to do molar mass. Not too bad. This is, I'm letting you know, one of the harder parts of thermodynamics, kind of the one of the most infamous. I don't really know why, but people don't seem to like these. So try to make sure you remember that. All right, let's practice. So when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85 degrees Celsius. What is the specific heat capacity of olive oil? What is its molar heat capacity? Okay. I'm not sure why I asked. Oh, got it. So I did not actually give you the molar heat capacity of olive oil. It turns out you actually can't find the molar heat capacity of olive oil. I just kind of added that on to make it a little bit more challenging. So we're going to assume in a little bit, I'll tell you what the molar mass is. It'll be 176.4, just because that's a random number. All right, so anyways, we are looking first off for our specific heat capacity, which we know CS is equal to Q over our mass times our delta temperature. Well, our Q in this case is 435 joules. Our mass is 3.4 grams. Sorry, my stylus really isn't working too well. And our temperature change will be our final minus initial, which is 85 minus 21. So we started at 21 degrees, rose to 85 degrees. So 85 minus 21, which is 64. I'm pausing just to make sure my stylus works. Anyways, let's calculate that out. So we'll get 435 divided by 217.6, which, when we plug that into our calculator, we get 1.999 or 2.0 joules per grams per degree Celsius. Those are the actual units of it. I know they're a little confusing, but they're telling us that basically it'll take 2 joules to raise 1 gram of it by 1 degree Celsius. So that's actually what it's meaning. So I'm going to write that somewhere, and then we're going to work on molar heat capacity. All right, so now we got to get to molar heat capacity, which again, we're just going to use this random molar mass of 176.4. This way I make sure you know how to use the formula. Normally they'll give you the molar mass, normally in this case they wouldn't have asked you the question, or the molar heat. So either way, they'll prepare you for what they ask you for. Anyways, our molar heat capacity is our molar mass times our specific heat capacity, which equals 176.4 times 2, which, when you multiply that out, you get 352.8 joules per moles times Celsius. That's it. You plug them in. So, yeah, hopefully that helps. All right. So welcome to your classroom practice. First example is you're finding specific heat. The second one, if you'd like a hard one, we'll actually be talking about this in a later unit. This is often people's hardest part. I really don't know why, but they really don't like these type of problems. So feel free to try this if you want. I'm asking for how much heat is absorbed when 500 grams of copper. That's the specific heat capacity, goes from that to that. Have fun. As always, thank you for watching.